Okay, let's start with a quick review of the DFT, which we talked about last time. So this is in section 8.5 of your book. And again, here we're interested in this point in using the DFT to approximate the Fourier transform. Okay, so let's say I have a x of t that is time limited, has a duration of tau, and then the corresponding Fourier transform of this I'll represent like this. So this is our x of omega. Although I'll find it convenient here to label the axis in hertz. And again, we'll say that the spectral width is equal to capital B. And then we know that the ideally sampled version of x of t, let me draw in the shape of x of t, the ideally sampled version, which we've called over bar of t, has Fourier transform x over bar of omega, where again we get replicas at fs, where again if our sampling time is capital T, fs is equal to 1 over t, and so what we get are replicas of the Fourier transform. And if we don't satisfy the Nyquist criteria, we'll have aliasing and some distortion at the higher frequencies at around fs over 2. And so this is what the spectrum of our ideally sampled signal looks like. And then last time we saw that, well, if we have a sampled version of x bar of omega, looks like this. This is fs, and these samples in the frequency domain are f0 apart. That leads to a periodic version of x over bar of t, where these replicas are now t0 apart, where t0 is 1 over f0. And so again, let me sketch in what my original x of t looks like. And then get some zeros. Again, these are samples. And the corresponding weights of these samples we call x of n. The corresponding weights of the samples in the frequency domain we call x of r. And to relate this to the f of t, to the DFT, there's actually, according to your textbook, using the notation in your textbook, the sequence x of n is not equal to just samples of our original x of t, but there's a scale factor involved that's t, which is t0 over n0. That's the number of samples between, in the frequency domain between 0 and fs, or in the time domain between 0 and t0. And then in this case, x of r, our x of r sequence is approximately equal to samples of the Fourier transform of x of t, where omega 0 here is 2 pi f0, or 2 pi over t0. And x of r and x of n are related then by what's known as the discrete Fourier transform. It's the sum from n equals 0 to n0 minus 1 of x of n e to the minus j r omega 0 n. This is known as the DFT, and it allows us then to calculate these samples of the Fourier transform from scaled samples of the time domain waveform, and then we can similarly calculate x of n from the x of r samples. It's 1 over n0 sum from r equals 0 to n0 minus 1 x of r e to the j r omega 0 n. This is the inverse discrete Fourier transform, wherein both of these formulas, omega 0 is, capital omega 0 is little omega 0 t, or it's 2 pi over n0. Okay. Last time we also talked about choosing appropriate values for our sample time, and then also our total time duration. From the Nyquist criteria, we know that our sampling rate has to be greater than twice the bandwidth to completely eliminate aliasing. So our sample time is 1 over our sample frequency. So we'll use this relationship to actually help find our sample time. And then T0 is equal to 1 over F0, where F0 is our desired frequency resolution. Okay. Now N0 is equal to T0 over T, or it's equal to Fs over F0. In the implementation, in the efficient implementation of the DFT known as the FFT, there are advantages to letting N0 be a power of 2. So often we might adjust F0 accordingly so that N0 is a power of 2. So in the next video we'll look at some properties of the DFT, and in the third video we'll actually look at some applications. One application in particular, using the DFT to calculate the convolution of two time domain waveforms.